Do we start again? Hmm? 1 minute? Okay.
Very good.
Okay, yeah, so first maybe I thought I should answer one question that I just got, and then I'll ask you if there's more questions about the previous lecture. So the question was, so in the last lecture I tried to argue that if you want to compute a scattering amplitude of some light particle, you don't have to worry about the heavy particles, and you can compute it from the time-ordered correlation functions of the light field that you derive from... that you derive from the correlation functions based on this effective action. And I said the effective action here should be local, so it should be integral d for x, and then maybe some kinetic term. And then some higher dimensional operators. Which I just wrote schematically like this. So anything you can build out of n derivatives in m fields, and then just by dimensional analysis, there should be n plus m minus 4. And the question was how to think of this this expansion. Should you think of this as some asymptotic expansion, or does it converge? And the claim is actually that this this expansion converges, and the reason is, or the argument is, that this expansion really corresponds to an expansion in momentum in the scattering amplitudes. And you know that scattering amplitudes are analytic in the momenta. So if you have in our example, we had the one pole here from the light particle from m squared, and then we had the cut at 4m squared, and then maybe there was another cut when we can produce two of the heavy guys. And we know that that this thing is analytic except for these poles and cuts, and so we have a finite radius of convergence, which translates into this having a finite radius of convergence. And what I wrote was that you can write the amplitude in the presence of this heavy particle as the amplitude where the mass is taken to infinity plus nm, and then here we have some coefficients, and then there's s or t or u to some positive power n, and then divided by n for m squared to the n. Now the one thing that I swept under the rug in this context was I assumed that these coefficients are actually independent of m, which also means that these coefficients are independent of m. This corresponds to saying that the discontinuity across this cut is a constant, and so the effect as you take the particle to infinity just goes away. You could imagine that the discontinuity across the cut grows with m, then the effect at low energies actually doesn't go away. And this would happen, for example, if you consider a diagram where you have a Higgs and then some top quarks or other quarks that get their masses through the spontaneous symmetry breaking, because you have a coupling, the Yukawa coupling here, Yukawa coupling here. This goes like 1 over m squared times y squared, and so the y, is m squared over v squared. And so naively there's a problem, but really you should just make sure that you keep the couplings fixed as you take the decoupling limit in this case. But so the statement really is that as long as you're not doing anything unreasonable and all the heavy particles decouple as you take their mass to infinity, this is actually a convergent expansion. So that was the answer to the question. And yeah, are there any other questions for the last lecture? Okay, if not, then let's start with this lecture. And we saw in David's lecture on the conformal bootstrap that symmetries play a crucial role for him. The same is true in effective field theory. The reason here is that, as I said, you should think of field theory as some tool that generates for you the most general S matrix compatible with unitarity, analyticity, and the symmetries you feed in. So eventually we'll have to understand how to write an action that realizes a given set of symmetries. Or for today, I'll just, not for today, but for now, I'll go the other way and just say if the action has a certain set of symmetries, what are the consequences? Some of the things were already discussed by David, so I'll be very brief, and then I'll need some other concepts or results for my later lectures, so I'll derive them now. So. And again, remind me when I'm writing too small, and feel free to ask questions. Okay, and so first, so we say we have a symmetry. Let's say we have a symmetry group G. Then we have some infinitesimal transformations on our fields that we can do. So we can send phi to phi prime equals phi, not phi prime, phi plus, and then some parameters, epsilon a, and then let me call it delta a phi, where the a's runs from 1 to the dimension of the group, and these things generate the group. So you have an action of the Lie algebra, if you want. We call it a symmetry if under this transformation transforms in this way. So we have d phi e to the is of phi, and then possibly plus a total derivative. This is for constant epsilon. And then if you take epsilon to be space-time dependent, but vanishing at infinity, this transformation means that you have d phi e to the I s of phi goes to d phi prime e to the is of phi prime equals d phi e to the is of phi minus I, well, that should be d4x j mu epsilon, or the derivative of this epsilon. So this is what I'll call a symmetry. And then in the classical theory, you know that this just means that this current is conserved. In the quantum theory, it gives rise to word identities that we saw yesterday. And I won't really derive them in detail because there were no complaints when David didn't derive them. But let me just say that the way you would derive them is you just write this thing in two different ways. So one, you just say, you can just change coordinates. So you have your path integral, maybe with some insertions. And on the one hand, you can just change the coordinates back to phi, so you can just eliminate all the primes. On the other hand, you can plug in the symmetry transformation and evaluate it that way and use it for the phi primes, use it for this, and then you get a word identity that looks like this. So you have d mu of the time ordered product of these currents, JA. And I should say, all these phis carry indices that tell you how they transform under this under the group action. I'll suppress all the indices, but you should think of all the phis having indices. I just don't want to have all the indices all over the place. I'll put them back when we actually need them. And this is, I think David called these what I call phis here, just he called them O's, but it's all the same. So you have some operators here in this time-ordered correlation function. So we have x, and then we have phi of x1, phi of xn, and this is equal to the sum over I delta of x minus xi, and then the time-ordered product of these guys with the ith guy replaced by the variation. And the variation has the index A. And if you look at what the derivative can act on, there's two things it can act on. On the one hand, it can act on the d mu j mu. On the other hand, it can act on the theta function here. And so you see that the way to satisfy this is if you, what this implies, because it has to be true for arbitrary insertions, is that we have d mu j mu of A is equal 0 as long as it's not near any of the other points or at any of the other points. And at the other points, what you get is you get the action of this thing on the theta function, which means you only get the time component, and you get a delta function from this. So you get delta and you get it for each of these guys. So you get delta x0 minus xi of 0. And then it gives you the commutator because you have both orders. And it's the 0th component, as I just said. And this is equal to the I delta x minus xi times delta A phi of xa. And if you want, what you can do is just integrate it to make it look more familiar. And we'll get that delta A is I commutator with the charge, where the charge is the integral over 3 space of this guy. Okay. Sorry, I also should draw a line at the bottom, I guess. This one actually doesn't move, I'm afraid. So okay, so it'll be convenient for what I want to do with the word identity to take the Fourier transform with respect to x and then take the limit as q goes to 0. So we have, okay, oh, here I guess I can go in the line. So we have integral d4x e to the I qx of and I act with a q mu, and on the other side e to the I q of xi from the delta function. And I may have got the sign wrong, I'm not sure, but let's fix it later. Now what I want to do is take the limit as q goes to 0, and in this limit I just get 1 here. And then what I can do, for example, is write this in terms of the commutator. And you'll see that you get the commutator for each of them. So really what you get is something like the charge, this had an A, commuted with all the insertions. Okay, so far so good. And then if I look at this, so I have two cases now that I want to look at in a little bit more detail. So first we can have unbroken symmetries. In this case, what I want is that my charges QA leave the ground state invariant, so the transformation leaves the ground state invariant, so the charges annihilate the ground state. And this means that this thing here just vanishes because we can pull the charge out. It acts on the left ones, it acts on the right ones. In both cases, it annihilates this thing. And then what you find is, if this is 0, it means that the Fourier transform of our time-ordered correlation function and let me change indices. So let me call the unbroken ones, so all of them for which this is true, let me call them I, and then we have the currents with the index I, and then phi of x so this is regular as q goes to 0. And it also means, if you look at this expression here, what this tells you is that all the Green's functions are constructed from invariant tensors of the unbroken subgroup H. So these generate and the correlation functions and S matrix elements. So here I'm assuming it's some global symmetry or internal symmetry. Okay. The other thing that should be clear, I'm already saying it here, that they generate an unbroken subgroup, is that so these are the charges, let me call the unbroken generators of the group GT. Then what we have is the Ti and Tj just give back another one of the unbroken generators. In particular, things like Fij, where these are the broken ones, which I'll talk about in a second, vanishes in this case. Okay, and then I guess is it okay to write here, or should I move to the other one, given that I won't be able to move it up? Yeah, but here the problem was, I guess, I should just stop writing here somewhere so people can read.
Okay, use the middle one.
Yeah, and I just end here, I guess.
There's another board.
No, but this one I already used, I think. Okay, so the next case I wanted to look at, actually, maybe let me write over there so I can really look at the formulas as I go. So if you look at the formulas now, the other option is that there is some So we have broken symmetries if there is any variation of one of these operators, delta phi I, such that this is not zero. And then what you might want to write, so I called them A just now, so what you might want to write is that this implies, and I put it in quotation marks, UA on the ground state is not equal to zero, because if it were, then this expression would have to vanish. The reason I'm putting in quotation marks is that this operator Q, strictly speaking, doesn't exist. It's not so much an interesting, well, depends on your definition of interesting, but it's really a volume divergence. So all the commutators of these operators with things still do exist, but the operator itself doesn't, so I'm putting it in quotation marks. The other thing it tells you, if you look at the top line, is that for this to be non-zero in the limit as q goes to 0, because the q mu is out there, these correlators actually have to have poles as q goes to 0. As momentum goes to 0. And we know from the LSE formula, or more generally from the pole structure or Fourier transforms of these correlation functions, that this implies that there is a massless particle in the theory. So we get a pole as we take q mu to 0, and because it's q mu to 0 where we get the pole, it means that there is a massless particle. And I'll call it number Goldstone boson, I guess, like everyone else. I haven't yet shown that it's a boson. I'll do that in a second, but let me just give it the name. Okay, does this make sense? Okay, one more piece of notation. So here I had my unbroken generators. For these guys, I have the broken generators. I'll denote them by X. X, and then I keep forgetting what indices I'm using. That's XA. And now we can ask what their commutation relations with with themselves and with the T's can be. And if you look at the commutation relation with one of the unbroken generators, then this is I, F, I, A, B, X, B plus I, F, I, AJ, TJ. But if we have a semi-simple compact group, then we can choose a generator so that the structure constants are totally anti-symmetric, so that this is actually vanishes for semi-simple compact groups. Furthermore, this is also true for anything that's related to these groups by analytic continuation. So if the complexification of the group we're looking at is the same as the complexification of a compact group, then this is also still true. And the last commutator we have is XA with XB, and here we have no more constraints, so this can be anything in general. So it can be an unbroken generator. You could also get a broken generator here in general. This one vanishes if it's a symmetric space. So if you have a space where you have a involution that's left invariant under involution, in this case under x goes to minus x. Okay, so this was some more nomenclature. Now let's look a little bit more at the structure here. So for any example I know, you can always find an individual delta phi. Delta phi A is not equal to 0. And then this equation simplifies. So we get limit of q going to 0 of q mu integral d for x e to the iqx. And then the only thing we have now is the field itself. So we have the time ordered product of the current corresponding to the broken symmetry, and then this field, let's call it at, well, it's, I don't know, let's put it at 0. And this is equal to, in my case, I think it should have come out with a minus sign, but it doesn't so much matter. So again, you can check to make sure you fix all the signs. So it should be you should get this equation. And now one thing we can try to understand is what kind of an object could this phi actually be. And first, notice that if we're not breaking any space-time symmetries, and our ground state is still Lorentz invariant, then this has to be a scalar, which also means that the phi has to be a scalar. The next thing we should understand is how it transforms under the group. In particular, we can try and understand how it transforms under the unbroken subgroup, because we learned that if we have an unbroken group, all the correlation functions have to be constructed from invariant tensors. The only invariant tensor that we have here really is delta, depending a bit on how you normalize your generators. But let me normalize them so that they're orthonormal. Then the only thing it can be proportional to is delta AB. So this actually has to have the same, or really the charge conjugate representation of this one. And let me just put the indices here, so we can have an index B here that is the same kind of index as this one. And so then this one is proportional to delta AB. This one is proportional to delta AB. And the only way to arrange this is if we have a state now. And again, I'm assuming that I'm not right now breaking a space-time symmetries. But the modification is not that big. You just have to interpret it a bit with care. But the statement then is that we need to have an overlap of J mu and phi with this one particle, with this massless Nambu-Goldstone mode. So we have J mu A of 0, P, let me call it C maybe, is I P mu, and then some constant here to fix the dimensions, delta AC, and this guy also has to have overlap with it, and because it's a scalar, and it's assuming it's an irreducible representation, there's only one constant that comes out, and so phi B of 0, we can just normalize it to 1. So this is one of the fields that creates one of these guys. And you see that this current, actually from this, the current J mu A of x is minus f d mu of phi I plus dot dot dot, and the dot 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 is actually important. In fact, if you have a non-abelian group, the only way to satisfy this your algebra is if there is actually something here And the existence of these terms means that these nonlinearly realized or these broken symmetries don't just imply the existence of such particles, but they also heavily constrain their interactions at low energies, which I'll try to discuss now. So are there any questions up to this point? Tom? Why is the pi on a pseudoscalar? This has to do... Oh, so here okay. Here I really just mean it has no Lorentz indices, so here I'm not being very careful. So yes, it can be a pseudoscalar. It really has to have the same charges as the current, as you can see. And so if the current is a pseudovector, then you will get a pseudoscalar. So here I really just mean it's not a vector or a fermion or something like this. It's a spin zero particle is all I meant. So and that also is not good because now it could be d mu of phi, so I didn't improve it, but you know what I mean, I think.
So the f that comes out, this is if I'm doing like QCD or something, this is like the pi on decay constant.
Yes. Mm-hmm. And yeah, as an exercise, I guess what you can do is just plug this in here and relate it to the broken. I mean, to the VEF. Yeah. I mean, it's really just this VEF. Okay. Any more questions while I wipe? Okay, so if there's no more questions, then let's try to use this statement to show that the interactions of these things are constrained at low energies. And for this, so this goes by the name of soft pion theorems, I guess. So there's a useful quantity that we can introduce. Let's call it 2 pi to the 4th. Let's put a delta function. So, okay, let me say what I want to do, though, before I write down the formula. So what I want to derive, and also let me get rid of the shadow thing. Yeah. So what I would like to derive are amplitudes, or the behavior of scattering amplitudes for emission of n soft, and let me call them these things. Let me call them pions because that's the most familiar example. In a process, general process, some alpha type, some particles going in, some particles going out, and I'll assume that these don't contain any additional soft pions. Other than that, it's supposed to be general. And then for this purpose, it's convenient to define a quantity that I'll call now 2 pi to the 4 delta of p beta plus q1 qn minus p alpha m mu1 mu n and then a1 an of q1 to qn as the Fourier transform e to the I q1 x1 e to the I qn xn, and then the vacuum expectation value of the time ordered product of a number of these broken currents. So this is mu1 a1 x1. Sorry, not the vacuum. Here I want the state. I want to go from alpha to beta. So this is state beta. Mu n an xn. And then here I have my state alpha. And before, to begin, I guess the simplest thing is to look at one soft pion. The reason I'm writing it in this way is because it will make it clear how to generalize it to n soft pions. I'll do one, and then hopefully I'll do two, and then it should be clear how to generalize it to n. So for a single soft pion, what we have is just 2 pi to the 4 delta of p beta plus q minus p alpha, and then we just have 1 mu, and then a of q given by integral d for x e to the iqx, and then beta j mu a of x. Now, what we know from our formula over there and the LSC theorem, so let me maybe give this thing a name. Let me call it J hat, or I don't know if there's a better term, but whatever doesn't create lead to pion poles. And then you see that this piece will have two contributions. One where this guy creates the external pion with the LSC theorem. So this will be I f q mu over q squared, and then the amplitude for the process we were interested in with one additional soft pion in the external state. So the fact that it's in the external state is because I chose a plus here. If you wanted to have it in the initial state, you would put a minus there. This is... and then there's a term, so this comes from the first piece in our current, and then there's a piece where we don't get a pion pole, and we get something that has the same index structure still. So we have n beta alpha. Let me put the index here, so the A, so we have all the indices there. Alpha, and here I should also maybe put the state. Of Q. Now, the other thing we know is that the current is conserved, so we can act with a Q mu on it, and this expression has to vanish. So and this implies, so if I act with a Q mu here, I just get I f m beta pi I alpha plus q mu n mu beta a alpha of q. And so if you take the limit as q goes to 0, if this this contribution is regular, you see that m vanishes. So if and this is typically called Adler zero. But in general, there's no reason for this to actually be finite in the limit as q goes to 0. So let's look at what the contributions are you might get from this. And so diagrammatically, what's happening here is that in our process, so we have our process with our state alpha and our state beta. And in this case, the current really attaches to a pion that's being emitted somewhere. So we have the current here, and we get a pole. On the other hand, there's also contributions. If you have nucleons in the theory, for example, or something that has a trilinear coupling, you also get contributions. So this is the contribution. This one is this guy, and this one, well, same state. This corresponds to having the current inserted in these external lines. And here you see that this can also lead to a pole in the limit where q goes to 0, because the propagator here goes like 1 over p plus q squared minus m squared of the particle. And this goes like 1 over, so the p squared cancels the m squared, and so as q goes to 0, you get 1 over 2 p dot q plus I epsilon. So this can also have poles. But the statement then is that the amplitude for the emission of a single soft pion either vanishes if this thing is regular, or more generally, the amplitude for the emission of one soft pion is dominated by the processes where the pion is emitted from one of the external nucleon lines. So this is the statement for a single soft pion. And this is already very interesting, but you notice that you don't learn anything about the group at this stage. So it just means that the amplitude is soft. So if you want to learn anything about the broken part of the group, you actually have to take multiple of these particles soft. And so let me try to sketch it for 2, and let me try to sketch it in a way that generalizes to n. And then what's the time? Oh, till 12. Okay. Okay, any questions again while I wait? Let's see. Okay, yeah, so let's look at the expression now for two soft pions. And let's right away start with this line, so we don't have to write down the delta function again. But there's 4 contributions now. So I have M, A1, A2, and then I have my other particles, mu1, mu2 of Q1 and Q2. And this can have a contribution again where both times we're using this guy, or we're using this guy once and then this one, and then we're using this guy twice. Plus, and then we have I Q mu over Q squared. Sorry, this was mu1. So we pick the first one to get the pole. And let me, for now, to avoid worrying about the case where I have 2 identical particles, let me take them different. So then I have this guy with a decay constant. And then for the other one, what I have is the amplitude where I now have one of these guys in the final state. Well, I chose my conventions differently, so I should have A2, and then I have beta, high, A1, alpha. But then where it attaches to the other line, and then I have the term where I'm picking both poles. With the scattering amplitude now with 2 pions in the external state. Okay. Now, this guy also appears in in this thing if my state beta contains one of the other pion, and we don't have to worry because I picked them differently, so there's no. So this again has a contribution where we're not picking the pion pole. Too small? Yeah, sorry. Sorry? Okay, I'll make them bigger. Sorry? Yeah, I'll make them bigger. Okay, and so the idea now is that I can use this equation to solve for n mu, plug it back in, and what I eventually want to do is I want to contract with two q's, so with q1 and q2, just like I did here, and take the limit as q goes to 0. So I want to do this again, and this means that if I plug this expression back in here, I get the mu, but when q acts here, it just annihilates this guy. And so the only contribution I get is this one with a minus sign. I get a minus sign from both of them. So I just get a relation now, m mu1, mu2, q1, q2, mu1, mu2, a1, a2, beta A is equal to, so I get this guy, q1, mu1, q2, mu2, and mu1, mu2, a1, a2, beta A, q1, q2, minus this guy. So and let me, I guess, cancel the minus with the i's. So I get plus, and the q's all cancel. F squared m So I now get a relation, or I have an expression for the amplitude I was interested in terms of this guy and in terms of this guy. This one, again, is the contribution where the pions are emitted from the nucleon lines. And then we have to evaluate this expression. And given the time, maybe let me just tell you what the answer is, and I'm happy to do it in more detail in one of the discussion sessions. But the upshot is from when you evaluate it, so you see that when you act with the q's on here, you're taking derivatives. If you're taking a derivative here, the current is conserved, so it will act on the theta function. It gives you a delta function times the commutator of the two currents, which gives a vector current. And so you get, at the end of the day, the scattering amplitudes are dominated where the vector current is inserted in the external lines. And at the end of the day, this means so this will have two contributions. One, again, is where the pion is emitted from one of the external, where they're emitted from the external nucleon lines. The other contribution will look like they're both emitted from the same line. And these kind of contributions, if you take the limit, and I'm happy to do it in the discussions, but if you take the limit, you can also kind of see it from the, well, let me not go because I haven't written down the Lagrangian for pions. But what will happen is that you get the amplitude of the underlying process. So it's m beta alpha multiplied, so by factors p I q1 minus q2 over pi q1 plus q2, and then the commutator of the broken generators and summed over all the external lines. So you're rotating all the external lines by this amount. And the denominator, I guess you can still see, because this propagator goes like 1 over p plus q1 plus q2 squared minus m squared, which reduces to this. This one we'll see comes from the derivative structure of the pion action, or the nonlinear sigma model. So I wanted to just derive these to show you that this really is something that all follows from the symmetry principles. And in principle, you can generalize this to the emission of n-soft pions. What you do is just you recursively rewrite all of these guys, the n's, in terms of the corresponding m's recursively, and then you can do have a relation between this one and the one where it's only emitted from the external nucleon lines, and then a bunch of the m's, which you can again solve for using or compute using a current algebra. So it all really follows from the symmetry structure. The nice thing about the effective field theories, once you've set them up, is that they really encode all of this. So you don't have to think. You just write down your field theory, you compute your scattering amplitudes, and they will correctly implement all the symmetries for you. So, and what I want to do next is, I guess, an example where we see some of these things in action. Are there any questions? Yeah?
So do you have to consider processes where you have arbitrary number of soft ion emissions to get infrared pions?
No, not for pions, I guess. I mean, they're not infrared divergent, the contributions. They're infrared, not divergent in 4 dimensions.
But if you're going to actually calculate a cross section,
but QED is different. I mean, we can look at soft emission for the photons, but it behaves differently. So there you really have to resum them because you have IR divergences. Here you have derivatives in your coupling, so they're actually soft. I mean, they're not blowing up the same way. Uh-huh. Oh, I suppose. I'm not sure. I know there's papers by Steve where he's trying to resum this. There's some way of exponentiating this, but it doesn't work as nicely as for the photons, because for the photons, what's nice is that they're abelian, I guess. So all the ways of attaching them at the end of the day just amounts, and if you resum over all the permutations, you get just 1 over p dot q to some power, and you can easily exponentiate this. Because it's a non-abelian thing, it's not that easy to resum. I mean, there's no divergence, so you don't have to resum for theoretical reasons at least, but I suppose you're right. So but I don't know. Tom, maybe no more.
You never use anything like this in a collider. The place you use something like this is usually more like
Here, yeah. Yeah.
I'm having flashbacks. When you do say scattering, I'm not going to say that.
Scattering lengths, yeah, I didn't talk about that. I mean, scattering length you would get if you're not deriving this guy, but you flip the signs. I mean, you can redo the same calculation with one of the pions ingoing, the other one outgoing, and then you take a nucleon line, and then you can derive the pion scattering length in exactly this way. But yeah, I'm not gonna do that. But it works in the same way. I really just wanted to illustrate that a lot of the structure is fixed by the symmetries, and we'll see that we recover this from the effective field theory also. Oops.
You're gonna go back to the left again.
Sorry.
It's very hard to see these indices all the way across the
I think it's a little less indices from now on. Okay, so now the next thing I wanted to talk about is really an example. So I'll talk about the linear and nonlinear sigma model. And we'll see a lot of these things in more detail. So the Lagrangian, the action I'll start with, is this minus squared, and the vectors are just n-dimensional vectors. So this has a global SON symmetry, and the ground state will break the symmetry without loss of generality. I can always choose my coordinates. So it's the first component of the vector that gets my VF. So let me choose let me call it chi, and let me call them xi, and this is now an n minus 1 dimensional vector such that this guy has a VF and the other ones don't. And so we can work out, so we can expand around that thing. So we write chi as, let's call it v plus rho, and then we just get the new action for this one is s is integral d for x. This is just the flat metric on our Rn, so this just gets 1/2 d mu and then rho, d mu rho, d mu xi, d mu xi, minus lambda over 8. And then this thing is the v squared cancels, so I get a 2v rho plus rho squared plus xi squared squared. And in particular, so if you square this, you find that. So just square this, you get a 4 with the 1/8. You get a 1/2 lambda v squared rho squared. So m rho squared is lambda v squared, and the xi doesn't have a linear term, so the m psi is 0. So this is just like we expected from our Goldstone theorem. So we get these n minus 1 massless guys. So these are our Goldstone modes, and then we got one massive guy. Now, one thing that's not nice, or let me first say the thing that's nice about these coordinates. It's not what's nice about these coordinates is that the measure, so the rho dxc is manifestly SON invariant for any reasonable regulator. You either put it on a lattice, or you impose a cutoff, or you do dimensional regularization. It doesn't matter which way, but this is invariant just because it's related to our phis. What's not so nice, of course, is that these x's don't only have derivative interactions, so it's not really manifestly clear that the amplitudes will be soft, as we discussed. It's true, so you can work with this thing, but it's just not a nice action. The other thing that makes this not very nice is that rho actually transforms under the SON group. It doesn't transform under the SON minus 1 group, but it does transform under the SON group, and this means it's non-trivial to integrate it out in this way. And the reason is clear. I mean, so also so So what we want to do is choose coordinates in such a way that the SON action is nicer. And it's obvious how to do it. I mean, here what we've done is we have in our field space, so if this is xi, and this is, I called it chi, then we've chosen coordinates in a somewhat weird way. We've chosen these Cartesian coordinates. But our group, the orbits of our group action are these circles or spheres in higher dimensions. And so what we should do is really use radial coordinates in this. And we should make sure that the coordinates, the transformation we should send chi to something that's linear plus stuff. And the same for the x's. And fortunately, so one set of coordinates we can use is just the spherical coordinates with a stereographic projection on the sphere. You can use any other coordinates on the sphere. I'll use those for now just because they cover the sphere everywhere except at a point. And given the time, maybe let me not go through the change of coordinates, and I'm sure you can also do that change of coordinates in any case. And so in our new coordinates, let me call them this. Let me call this rho prime maybe. So we get this system of coordinates, and of course we can rewrite it. Oops, sorry. Forgot the most important piece. Just from the metric of the force sphere, you get the rho prime squared here over v squared. And if we shift the thing, so with rho prime is sigma plus v. So we get this action, and now sigma really is invariant under the SON action, which is good because we can now integrate this guy out. These guys are manifestly still massless. The one price we paid is that there's a functional determinant from the change of coordinates. And for a second I'll keep it, and then I'll tell you why or for what regulators you can throw it out. Yeah? Yeah, let me maybe just write down the determinant and say when you can throw it out, and then yeah, then I think it's a good time to just take a break.